This month's calculation video is about the ideal gas equation, in particular, how we apply it to more challenging questions and examples that involve other mole calculations. So let's make sure that we remember what the ideal gas equation is telling us. The basic equation is P, pressure, multiplied by V, volume, gives us the number of moles times temperature and the gas constant, which should be given to us in the question and is equal to 8.31 joules per mole per Kelvin. Pressure and volume are on the same side of the equation. This makes sense because they're sort of inversely related to each other. So if you decrease the volume, you will increase the pressure and vice versa. On the other side, the number of moles, obviously the more particles there are, either the more pressure or the more volume. That depends on whether your container will expand or whether it's a fixed wall container, in which case the pressure will increase. And temperature is on this side. Again, the higher the temperature, either the pressure will increase if the container can't move its walls, or the walls of the container will expand and the volume will increase. If you think about if you heat a balloon, for example, full of gas. Units, really important in the ideal gas equation, one of the key ways that students make mistakes. And so we need to remember that pressure is in pascals, volume is in meters cubed, number of moles, of course, is just our normal unit, and then temperature is measured in Kelvin. So we need to be able to rearrange this, and one of the most likely ways that we have to rearrange it is to find moles. Now that's easy enough if we just want to find the moles directly, given the other variables. But the other thing that will happen is that we are given the mass and then expected to find the number of moles and therefore the molar mass of a particular substance. And if we can find the MR, or the molar mass, it also means that we might use this equation to actually identify the formula for a gas, given a bit more information. So here is our much more applied example. We've got an unknown compound, which we know contains carbon, hydrogen and oxygen, but we don't know the formula. And then we're given two separate pieces of information. The first one is about the mass of the sample being vaporized, and we're given a volume, a pressure and a temperature for that situation. We're then told that a separate sample of this particular compound combusts, and we're given the mass of carbon dioxide and the mass of water produced. And from all of these, we're expected to find the molecular formula. Now, this would potentially be a 7 or 8 mark question. Or, if you're lucky, it will get split up into a few sections to make it easier to work out what it is you need to do. So, if we want to know molecular formula, there are two pieces of information that we need. We're going to need to know the empirical formula, so the simplest ratio, and we also need to know the molecular mass, or we might call this MR or even RFM. Now the word empirical formula actually means, we're getting it from measurements, and the empirical formula can be found by the information about carbon dioxide and the water, and the molar mass or the molecular mass of the gas can be found using the information about the ideal gas, because we can find the number of moles and we have the mass, so we can rearrange it because we know that moles equals mass over MR, and therefore MR equals the number of grams, the mass, divided by the mole. So MR is in grams per mole, although we don't always include that unit when we're calculating it. And so, for example, if we knew that the empirical formula was CH2 and the MR was 42, we'd be able to put those two pieces of information together to know that the molecular formula was C3H6. And we do that by adding up the 12 for the carbon, the 2 for the hydrogen, which equals 14. We do 42 divided by 14, which equals 3. And that is how we get to our molecular formula. So let's apply that to this question with a little bit more maths involved. And we're going to do the ideal gas bit first. So we're going to use the relationship we just mentioned, MR equals mass divided by moles. We know the mass. We're going to calculate moles using PV equals nRT. Always write out the ideal gas equation before you start converting units and putting the numbers in. Two reasons for this. One is it makes sure that you actually take the time to rearrange it correctly. And the second is that the rearranged version is often worth a mark in exam papers. So even if you get some other unit conversions wrong. Next thing we're going to do is substitute numbers using the correct units. Write this out again because sometimes you get a separate mark for conversions. So don't just throw it all in the calculator and hope for the best, because if you're just one number wrong, then you've messed up everything and you don't get any of your working out marks. Okay, so P for pressure. Pressure is already in pascals, so I'm going to leave it as it is. V for volume. Volume is 234 centimeters cubed. We need to divide by 1 million, or 10 to the 6, and that gives us 2.34 times 10 to the minus 4 meters cubed. Remember, meters cubed is a huge volume unit, and so your volume in meters cubed should be a pretty small number. On the bottom, we've got the gas constant. Temperature needs converting to Kelvin, so I'm going to get my 200 degrees C and I'm going to add 273 to get 473 Kelvin. Now we can put all of that in the calculator and we can calculate the number of moles. And the number of moles, N, is equal to 6.55 times 10 to the minus 3. We're now going to plug this into our equation for MR. MR is mass over number of moles, so it's 0.406 over 6.55 times 10 to the minus 3, and that gives us a molar mass of 62, a sensible number for the mass of a gas. So how do we do the next calculation? There's a number of ways we can do this. So we're using the second piece of information, the information about combustion. We know that this sample of compound A is combusted, and we do actually know the molecular mass. So one thing that people might sort of jump into is think, well, I've got the mass there, 1.86 grams, and I also know that the MR is 62, so I could work out number of moles. We could do it that way, but actually it's not that helpful because we don't know the formula of A. So there's not much we can do with the number of moles. Instead, I'm going to show a method that just treats this as if it were a separate question. So as if we didn't have the MR and the question was just asking you from the information about CO2 and H2O to work out empirical formula. And that is because that is a really common question. So we might as well know how to do it. So we know that it contains carbon, hydrogen, and oxygen. And what we want for the empirical formula is the molar ratio. So basically what we need to know is how many moles of carbon, hydrogen and oxygen are in my 1.86 grams sample. And all of this is simply using the relationship between mass and moles and relative formula mass. That is it. So the first thing we can calculate is the moles of CO2 and the moles of H2O, because that is what we have the mass of. So I know I have 0.72 grams of CO2 and 1.62 grams of water. If we divide 0.72 by 44, which is the MR of CO2, then that will give us 0.06 moles. And then if we divide the divide the 1.62 by 18, which is the MR of water, that gives us 0.09 moles. Okay, this is why at the first step we need to be a little bit careful, because we could just be going, right, okay, the ratio of carbon to hydrogen is sort of 6 to 9 or 2 to 3. However, these are the moles of carbon dioxide and water, and we want the moles of carbon compared to hydrogen, not carbon dioxide compared to water. So the next step we do is my moles of carbon and my moles of hydrogen. Now it's almost the same. For carbon dioxide, it is the same. If you have 0.06 moles of carbon dioxide, you will have 0.06 moles of carbon, because there's 1 to 1 in the formula, because it's just CO2. But if you have 0.09 moles of H2O, you have 0.18 moles of hydrogen in your compound. So that's actually what we have in terms of our ratio. Now we could simplify that up now if we wanted to, divide by both sides by 0.06 and see that I have a 1 to 3 ratio of hydrogen. However, we're jumping ahead a bit because we still don't know how much oxygen we have. So there's not a great deal of point. We actually just know at the moment that in my 1.86 grams sample of A, I have that many moles of carbon, that many moles of hydrogen. So what do I do to find the moles of oxygen? Well, we need to work out the moles of oxygen. And again, I'm going to use a method that works when you don't know anything else about the compound. We have 1.86 grams of our sample A, and we know that this is made up of carbon, hydrogen, and oxygen. We also know that this is made up of 0.06 moles and 0.18 moles, and we don't know the moles of oxygen. We do know the whole thing weighs 1.86, and we do know the relative atomic masses of carbon and hydrogen. So what we can work out is the mass in grams in this particular sample of carbon and of hydrogen. So take 0.06, I'm going to times that by 12, which is the atomic mass of carbon. That gives me 0.72 grams in my original sample. The mass of hydrogen is just 0.18 times 1. So remember, this is hydrogen atoms that we're looking at because it's in a formula. We're not looking at H2 gas. So the mass of oxygen, and again I'm writing O deliberately because it's just oxygen atoms that I'm measuring, is going to be the mass of the sample, take away the mass of the carbon, take away the mass of the hydrogen. And that is going to give us 0.96 grams. Pop that in my information up here, 0.96 grams. How many moles does that work out at? I'm going to divide by 16 because that is the atomic mass of oxygen. And my answer to my question mark is going to be 0.06. So it turns out that the molar ratio is 0.06, 0.18, 0.06. Divide everything by 0.06 and I get my final simplest whole number ratio as 1 to 3 to 1. So the empirical formula is CH3O. We're now ready to put all of that together into our final answer. So we know the empirical formula is CH3O. We know that the molar mass is 62. Add up 12 plus 3 plus 16. That gives me a mass of 31 for the empirical formula. Times that by 2 gives me 62. And therefore the molecular formula is C2H6O2. And that's how you do it.